This is the outline. So we'll see what is spice, and there are several simulation options. So DC analysis and transient analysis. These are two most popular. In digital, that is good enough. But for analog circuit designer, you may need additional different variety of the simulation mode. We need to understand what is a sub-circuit and how we optimize this. How we optimize the circuit and how we measure the power, so we can compare some logical effort from the simulation result. The SPICE is the abbreviation of a simulation program with integrated circuit emphasis that is originally developed in 1970s at Berkeley. So many commercial versions are there. So in our lab, we mostly use the Spectre from the Cadence. The H-Spice is robust, the most popular. Now the Spectre is also widely used. The H-Spice is supported by Synopsys. The company name is Synopsys. The Cadence supports the Spectres. So the old days that was written in part1 for punch card machines, but nowadays we don't do that. So sometimes we call circuit elements called cards, but this is a kind of old term. So we will usually we use the SPICE stack is kind of the written description of the circuit. That is called SPICE stack. We often this is about how you write the device a SPICE stack, and it is like writing a program. First you have to plan to sketch. This is the planning stage and actual coding stage and testing stage there. So first you sketch schematic on paper or in editor using GUI. And most of the GUI program you are using just give lots of the easiness for writing or drawing a circuit. Once the circuit is drawn, we need to generate the actual the list by coding or automatically generate by the program software. In case you want to write a code, you start with you put some generous comments there, and then when you test, you just predict what the result should be, right? Instead of checking what the result will be. So output, the purpose of the simulation is checking the result versus what you expect. Without expectation, the result from simulation seems like a garbage, because you may put in the garbage, so you may expect the garbage out. So always it is important, always when you test a circuit using simulator, you must have some concept of what the result will be. Whether that result is expected or not, you need to determine, you must decipher what the simulator result, right, is. So that's the most of the student making a mistake. They trying to get the sum. They rely on the simulation too much, because in such case, student may set up the simulation environment not properly. right? So you have to be aware of what the result should be before you actually simulate. This is an example of a spice deck. We have a simple voltage source here and resistor and capacitance. So we have three components in network, so we define three, 1, 2, 3. First one is the module name here, and this is a net definition. So in is this net name of the net, and GND is the name of net here. PWL in input and output. This is the instance name, and this is the module, the sub-circuit name. So we use the PWL with the instance name of a Vin. So this is instance name, all instance name. So R1, RC1, and Vin, and these are the net name, right? So this is the property of the resistance, 2K and 100 femtofarad of the C1. So according to this, we know that this node is in and this node is GND and this is out. So each node we define the net name here. So we have three components here. So Vin is defined as the PWL, that is piecewise linear voltage source. At 0 picosecond, at time 0 we have a 0 voltage, and time 100 picosecond we get the 0, and time 150 picosecond we have a 1.8. So you connect them, you get this kind of waveform there. This is the 100 pico, and this is 0.150 picosecond, and we add the 800 picosecond, we stay. Let's continue the keywords at the after this stimulus part. Stimulus is the some keyword. Stimulus. This part is to provide some command or message to the simulator. So it starts with the dot command here, dot trend. It means the transient simulation. 20 picosecond is the time step, and 800 picosecond is the simulation period, simulation time. So if you run this, run the transient simulation, then every 20 picosecond it evaluates the signal value. Every 20 picosecond, this is a time step, right? And then it evaluates up until 800 picosecond. This is simulation time. The sim time. The next keyword is the dot plot, meaning we want to monitor voltage of the input node and voltage of the output node. We have an input node here in, sorry, this is the input node in, and we have output node out, right? So this is the output node, and this is the input node, right? In. So we want to plot the output. That end is the end of the simulation circuit, SPICE input circuit. Okay. This is the result of the y-axis is kind of time. We get the output shown here like this. Kind of a behavior is we get. For the input, we see the A like this. Input comes in and output comes out, something like that. So this is kind of an example of the output. So RC, simple RC circuit. This interface is a very old time output. So nowadays we have a more beautiful output plot rather than like this, right? This is just an example. Shown here is a graphical output. As you can see, we have input coming in and the output comes like RC network. Sources. There are a different variety of the sources defined in the simulation. We have for example, we have a DC source defined like this. You start with the character V, and this is the name of the nodes and the value property of the DC voltage, that is 2.5 volt. We also have a piecewise linear source called PWL. So we define PWL with the instance name of the Vin. Between input and ground node, we have all the piecewise voltage information on the right. Okay, we can have also pulse the source. This is pulse is the keyword that we say that this is pulse the source. This is the name of the voltage. Pulse the source, instance name, right? Instance name. This is a net name between two nets. Right hand side is the kind of property. So for example, for pulse we defined like V1 and V2 and TD and rise time and fall time and pulse width, etc. like this. So we define these value on the right and then define V1 and V2 here, right? So this is a kind of a pulse. PER is a period of the pulse, right? So we define also period here. We can repeat this pulse with the period argument here. This is just an example that used in actual lec7Spice here. There are a variety of the SpiceNet elements. We want to represent all kind of electrical components, resistance, capacitor, inductor, and etc. Right? All these letters represent each element. There's also widely used unit for the electrical signals. A is the atto, 10 to the power of minus 18th, and femto is 10 to the power of minus 15th, and pico. So pico, femto, nowadays atto is quite now getting used to it. So, and nano is quite popular nowadays, and the micro and milli. So the milli 10 to the minus 3, and kilo 10 to the power of 3, mega 10 to the power of 6, and giga, right? So all these the units nowadays widely used. So you have to be comfortable with this unit. So example, 100 femtofarad capacitor is 100 femtofarad. So F is the 10 to the power of 15, right? So 100 times 10 to the power of minus 15, like this, right? Times 100. So you better get used to it, okay? DC analysis is based on non-moving signal. So every input on this on these all these net that not moving, and so staying at DC, the staying at the stable voltage level. So the purpose of the DC analysis is to identify the operating point of the transistors or the devices. So let's take a look at the DC analysis example. So here it starts with include statement that include the model parameters. So we have the transistors here, right? So transistor model is included. The temperature is 70 degrees C, and option is the post that is used for the spice. So that option is not, I'm not sure. So let's move on. So it start with the VGS. The V start with the V means this is the instance name for the voltage source, right? So VGS is between G node and ground. We apply the 0 volt. Another voltage source, the VDS, between drain and D node and then ground is 0. So according to this the schematic, so this gate voltage G, this is G and this is G and D, and drain is D node. So M1 is, there's M1 device. M, if that starts with M, that means transistor. So that the name of the transistor is MOS here. So DG, GND and GND is the transistor net. So the first guy is drain, and the second guy is the gate, third one is the source node, and the fourth node is the bulk body connection, right? So although it looks like there's no body here, there is the body explicit body net there for the transistor. So that is connected to ground. The width of the transistor is 0.36 micron and length is 0.18 micron. So once we construct the shown this network, then we add some command to let the tool know what kind of simulation should run. So .dc .dc command here tell the simulator to run the DC analysis. So .dc, so VDS, the voltage name, this instance name VDS is flipped from 0 1.8 0 to 1.8 with the step of the 0.05 volt. So 50 millivolt step is flipped at 0 to 1.8. There's a flip command here, right? And then also the VGS also flipped from 0 to 1.8 with the step of a 0.3. So it sweep the voltage, right, for the node. So and then find out the electrical property of the biasing point of this transistor. For example, the current level and operating point kind of thing. So we, in order to identify the operating point, we must run the DC analysis. For most of the case, digital circuit, we usually don't run the DC analysis because we don't usually care about the operating point of the transistor. But when you design the amplifier, analog amplifier, we must ensure that the transistor in saturation most of the time. In some transistor may fall into triode region, it may be intentional or unintentional, so we must identify whether that is intended case or not. So in analog, most of the analog circuit, we have to run the DC analysis first. But most of the students start with the just transient simulation, but the transient simulation doesn't give us any information on the device operating point. So when you run the analog circuit, you must run DC analysis first. Let's take a look at the output from this the comment Spice deck. So from the previous Spice deck, we swapped the VDS from 0 to 1.8 with the 50 millivolt step, and also we swapped the VGS from 0.6 to 0 to 0 volt to 1.8 volt. So if you plot this IDS current through the device, then you will see like this kind of a typical transistor current curve. So as you can see, beyond a certain point, the current is stabilized, the current is fixed, so it looks like a current source, right? But below a certain limit, this current linearly increasing over VDS. So this is a triode region. So it looks like a resistor, right? So that's why we call it triode region, and this is the saturation region. Okay, so we can identify the operating region, and also there's in the tool. So in the if you look at the one of the parameters, look at the device parameter, it reports the operating region. So region, this is region 2 and region 1, something like kind of stuff. So you can actually look at region, operating region that is reported from the tool, right? Okay. Elements defined with the M element, the M with the name, and drain, gate, source node, and body, and each type, whether that is PMOS or NMOS. And also we have a WL definition, and area of the source. AS is area of the source, AD is area of the drain, PS is perimeter of the source, and perimeter of the drain. All these are described, right? So you can, and this actually define the characteristic of the transistors. This is a transient analysis within including MOSFET design. We have input and NMOS and PMOS. We have also supply voltage VDD here. So we have 4 instances here, 1, 2, 3, 4. Each one, this is VDD, and this is the input, and this is transistor M1 and M2. Right? So we are using the transient with the 1 picosecond time step for duration of 200 picosecond. Right? The output, you see like this kind of a pulse input, you get the overshoot like this, right? This overshoot comes from the input output parasitic, so parasitic capacitance there. Because of this feed forward capacitance, we get this some of the input a sharp, edgy whenever input changes sharply, the output will follow the input, right, momentarily. This is very fast edge. For that case, you get this kind of glitches.